So I'm going to start by looking at this picture. There's a curve here, and it's the same curve repeated 4 times. We're trying to estimate the area between the curve and the x-axis every time. Here we used 4 large rectangles to do it. Here we used 8. Here we use 16, and here we use 32. You can tell that the 32 rectangles are going to give us a much better approximation of the area between the curve and the x-axis than the 4 rectangles. So the more rectangles, the better. How do you get a better estimate? Use more rectangles. Okay. How many rectangles would be the best? The best amount of rectangles would be infinity. So that's what I'm going to kind of use that idea to talk about finding exact area. So again, here 4 rectangles, 8, 16, 32. The more rectangles, the better. So an infinite amount of rectangles would be the best. Another way to look at it is here we had a wide base to our rectangle. Here the base is half as big. Here it's half again as big, half again, half as big again, and then here same. So every time we make the base of the rectangle smaller, we get a better estimate. So what would the ideal base size be? 0. All right, now we're going to look at some definitions here of Riemann sums. So there's nothing really to write here. We're just going to talk. So Riemann sums is the technical definition for finding area using rectangles. So you can see we're adding up, because it's a summation, we're adding up rectangles where f of C1, that would be the height of every rectangle, and then delta x, that would be the base of every rectangle. So this is a technical definition of what you did in your homework, finding area. And here we are going to work towards, using Riemann sums, we're going to work towards finding the exact area under a curve instead of estimating. So, you know how I was saying it's best if we had an infinite amount of rectangles, or our base of our rectangle would be as small as we could get it. Here we introduce the idea of a limit. We would love for the base, which is delta x, we want that to be as small as possible, so we take a limit and we have it approach 0. Doing that says we're trying to approach a number of rectangles that's so high that the base of every rectangle is 0. You can't have it be 0 because a line doesn't have area, but you can start it with some width, and then you move it with a limit to be 0. So the definition here is the area of all of these rectangles, height times base. If the base is going towards 0, it's defined by an integral. So we are going to use integrals to find exact area. I'll show you how to do that in some of our examples.